Question 2, we're looking at interference. Seed shrimps live in the soil in New Zealand forests. Male seed shrimps have an unusual type of mating signal. The hairs on their antennae act as a diffraction grating, and during courting a male seed shrimp will move his antenna, causing other seed shrimps to see a flash of coloured light. And there's a missing picture here which would have explained it in a bit more detail. Now, all of that is pretty much irrelevant. You can practically ignore the entire thing. It's a context, it's interesting to know, but it doesn't help you answer any of the questions. And it could confuse you if you're trying to understand it. So it's good to be able to filter some of this information out. Anyway, moving on. Question A. When the white light is incident, that means it's shining on a diffraction grating, the light is split into several spectra, with higher order spectra occurring at larger deviations. State why white light is split into a spectrum when it goes through a diffraction grating. Okay, this is a good place to lay out the formula that we use. N lambda equals d sine theta. Now, white light is light that's made up of many different wavelengths. So this wavelength here is going to be different for all of the different parts of the light. And that will, the d is the spacing of the lines on the diffraction grating, and sine theta, or theta, is the angle through which the light is diffracted. So if you increase the wavelength, or decrease the wavelength, whatever you do, if you change the wavelength, you'll change the angle that it diffracts through. So that's how a diffraction grating works. White light, many different wavelengths all bound up, will cause different angles and therefore of diffraction, and therefore separate out the colours. Okay, part 2. Explain which end of the spectrum is furthest out from the central position. Okay, well, we can see from the equation above that if you increase the wavelength, let's just draw an up arrow instead, that means we're going to increase the sine theta term, because N and D don't change when we're considering just the one single spectrum. And so the longest wavelengths will diffract the most, and that happens to be the red end of the visible spectrum. B. Explain the effect of decreasing, here we go, the diffraction gratings of different shrimp species have different slit separations. B. Explain the effect of decreasing the slit separation on the number of spectra produced by the diffraction grating. Okay, you can do this mathematically. Remember, d lambda equals n sine theta, n lambda equals d sine theta. Assuming n and lambda don't change, if you decrease d, so those are no change, decrease d, you'll have to increase the spacing for that same thing to work, for it to work in the same way. Okay, does that make sense mathematically? The left hand side stays the same, no change. The right hand side has to also stay the same with no change. So if one goes down in a decrease, the other part has to go up. Sine theta will increase. And because sine is just a function operating on theta, that will cause theta to change. Now, getting specifically into the question, we're looking at the number of spectra, not just the angle. But if, as the light's coming in, here's your diffraction grating, if theta is increasing, so the angle that it's diffracting is increasing, that means there will be less spectra. If you consider each one of these lines as a spectra, as theta increases, you're going to lose the ones that go beyond 90 degrees out here. So you'll have less spectra produced. C. The hairs on the antenna on a particular shrimp create a diffraction grating with a slit separation of 6.6 times 10 to the minus 7 meters. By attempting to calculate the angle through which light of frequency 4.25 times 10 to the 14 Hertz is diffracted in the first order spectrum is n equals 1, explain why this colour will not be present in the spectrum produced. So that's the big question. We're trying to explain why this colour will not be produced. And just going back up above, we were talking about how as you increase theta, you lose these external fringes. So it's highly likely that we're just dropping off the colour that those yeah, we're losing those ones off the end. Anyway, moving on. I've got a lot of noise distracting me at the moment from outside the classroom. I'm very sorry. Carrying on. So we have to do the calculation. N lambda equals d sine theta, and we're trying to find theta. So n is 1. We've got the slit separation, or what have we got? The light of frequency. Remember, that's a frequency here, so we have to use our wave equation, v equals f lambda, and rearrange to find lambda. So lambda equals v over f. V is the speed of light, which is 3 times 10 to the 8 meters per second, and frequency was given to us up there, the 4.25 times 10 to the 14. And d is what we're trying to work out. Let's just put this in here. We've got n times v over f equals d. We're trying to calculate the angle, sorry, sine theta. D is the slit separation. There we go. So what we would have to do is rearrange this for sine theta. So we're going to rearrange that. We'll have sine theta equals n v over f, and all of that is going to be divided by d, and then we would just plug all of our numbers into there, calculate to find theta, and if theta is greater than 90 degrees, then we can then we've got our answer. We've explained that the colour is not present because it's greater than the 90 degree angle which the diffraction grating can bend. Okay, I've been interrupted by the bell and students pounding on the door, so I will continue this in a second part at a later stage.